In this episode, we're going to rehearse network security architecture the way you would rehearse directions before driving somewhere unfamiliar, because remembering the route matters as much as understanding the map. You have already learned about segmentation, security zones, firewalls, proxies, remote access, and zero trust, but now we want fast recall and strong instincts. The goal is to be able to hear a description of a network and immediately picture where the boundaries should be, what controls should exist at those boundaries, and what mistakes tend to show up in real environments. We will do that by replaying a few common network patterns as a spoken walkthrough, and then calling out misconfigurations that quietly undermine security. As you listen, keep asking yourself a simple question. If something bad happens in one area, what stops it from spreading everywhere else? Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start by rebuilding the core purpose of network security architecture in one plain idea. Architecture is about shaping where traffic can go, not just reacting to bad traffic after it arrives. Segmentation divides systems into groups that make sense, such as user devices, servers, and sensitive data stores, and security zones label those groups by trust level. Controls live at the boundaries between zones, because boundaries are where policy becomes enforceable. If you have no boundaries, you have no meaningful places to apply consistent rules, and that usually leads to an environment that is easy to move through once any single device is compromised. The reason we keep coming back to segmentation is that it reduces blast radius, which is just a calm way of saying fewer things break when something goes wrong. When you can describe the zones and the boundaries out loud, you are already doing the most important part of architecture. Now recall the first major class of controls, which is traffic enforcement. Firewalls and similar boundary devices control which connections are allowed between zones and which are blocked. The best beginner mental model is that a firewall is a policy checkpoint that decides whether a conversation is allowed to start and whether it is allowed to continue. Modern firewalls can be more aware than simple port and address checks, but the real security value still comes from the policy you define, not from flashy features. A strong policy is usually specific about who can initiate connections, where they can go, and what they are allowed to reach. A weak policy is vague, overly broad, and full of exceptions that nobody can explain later. When you think about enforcement controls, think about allowed pathways that have a clear reason to exist and denied pathways that reduce risk without breaking the business. Add the next class of controls, which is mediated access. Proxies can act as controlled intermediaries for outbound web access or inbound application access, giving you a consistent place to apply rules and collect logs. This is valuable because many risks arrive through everyday web usage, and many sensitive services should not be exposed directly. A proxy is not just a middle hop. It is an opportunity to enforce policy at the moment a user or an external client requests something. If you route traffic through a proxy intentionally, you gain visibility into destinations, patterns, and unusual behavior that would otherwise be scattered across endpoints. For beginners, the key retrieval point is that enforcement is about allowing or blocking flows, while proxying is about shaping how flows occur and what you can learn from them. Together, they help turn a network from a collection of cables into an environment with guardrails. Now rehearse remote access controls in a way that connects back to zones and boundaries. Virtual Private Network, VPN, solutions create encrypted tunnels so remote devices can reach internal resources. But the architectural question is never just can they connect. The question is what they can reach once connected, and whether that access is narrow, intentional, and monitored. Multi-factor authentication, MFA, strengthens the identity check for remote access, but it does not automatically enforce least privilege after the user is inside. The safest designs treat remote users as entering a specific zone with specific restrictions, not as becoming fully internal citizens with broad access. If remote access drops a device directly into a wide-open internal network, the tunnel becomes a powerful pathway for attackers who steal credentials. Your retrieval cue here is simple. Encrypted tunnel plus strong authentication is necessary, but segmentation and authorization are what limit damage. Bring Zero Trust back into the story as a way of tying these controls together. Zero Trust is not one box you buy, and it is not a slogan about distrust. It is a practice of verifying identity and context for access decisions, using least privilege, and assuming that breaches can happen. The network becomes less about inside versus outside and more about which request is being made, by whom, from what device, to which resource. That mindset pushes you toward granular access, stronger internal boundaries, and more consistent logging. In a zero-trust approach, you still use segmentation, firewalls, and proxies, but you apply them with the assumption that internal traffic can be risky too. Force-based retrieval. Remember that Zero Trust operationalizes trust as conditional and temporary, which means architecture must support frequent verification and tight scopes of access. Now let's shift into the second half of the walkthrough, which is recognizing common misconfigurations that quietly break these good intentions. The most common failure is a flat internal network, where everything inside can talk to everything else. This often happens not because people want it that way, but because it feels easier during growth and troubleshooting. Over time, exceptions pile up, and eventually the network has only one real boundary, the perimeter. In that world, a single compromised workstation can potentially scan and reach many internal servers, which makes lateral movement easier. Even if the organization has strong perimeter controls, the lack of internal boundaries means the environment behaves like one big zone. When you hear that users can reach anything if they know an address, you should immediately suspect missing segmentation or overly permissive internal rules. A second misconfiguration is confusing segmentation with naming. Teams might create many subnets or many labels, but still allow broad connectivity between them. This looks like structure on paper, but behaves like a flat network in practice. The purpose of segmentation is not to create neat diagrams. It is to reduce unnecessary pathways. If every segment can initiate connections to every other segment, the segmentation is mostly cosmetic. This misconfiguration often shows up as rules that say allow internal any to internal any, or broad groups that include far too many systems. It can also show up when zones are defined, but boundary enforcement is missing or inconsistent. Your retrieval test is to ask if a device in a low-trust group is compromised, what stops it from reaching the most sensitive systems? And if the answer is basically nothing, the segmentation is not real. A third misconfiguration is overly permissive outbound traffic, sometimes called weak egress control. Many environments focus heavily on blocking inbound threats while letting internal systems connect outward freely. This matters because compromised systems often need to communicate outward to receive instructions or send stolen data. If any device can initiate connections to anywhere on the internet, unusual outbound behavior is hard to spot and easy to exploit. Tight egress controls do not mean blocking the internet entirely. They mean making outbound behavior predictable and limited based on system role. User devices might browse the web through controlled pathways, while servers might have very narrow outbound needs. When you hear that outbound traffic is mostly unrestricted because it is too hard to manage, that is a clue that the architecture may be missing an important containment layer. A fourth misconfiguration is relying on default or broad trust relationships, especially around remote access. If a VPN connection drops a user into the same zone as internal workstations, that user might inherit access that was never intended for remote contexts. Split tunneling can also create a bridge between untrusted local networks and internal resources if not carefully managed. Another common issue is allowing remote access based only on a password, without MFA or meaningful device checks, which raises the risk of credential theft leading directly to internal access. Even when MFA is used, permissions often remain too broad because role-based restrictions were never enforced after connection. For recall, think of remote access as an entry door to a specific zone, not as a teleportation device into everything. If remote users can reach more than they need, the architecture has extended trust too far. A fifth misconfiguration is inconsistent logging and visibility at the boundaries. Controls that block or allow traffic without generating usable logs are like doors with no record of who walked through them. When an incident happens, You want to reconstruct who accessed what, when they accessed it, and whether that behavior was normal. If boundary enforcement points are not logging meaningful events, investigations become guesswork. Another version of this problem is logging too much low-value noise and too little high-value context, which makes it difficult to find the real signal. Proxies, gateways, and boundary devices are natural observation points, but only if they are configured to record what matters. The retrieval habit here is to always pair an architectural control with the question of how you will know whether it is working and how you will detect misuse. A sixth misconfiguration is exposing management surfaces where they do not belong. Many systems have administration interfaces that should be reachable only from restricted management zones, not from general user segments, and certainly not from the internet. When those interfaces are reachable too broadly, attackers who compromise a user device can often pivot into administration functions quickly. This can happen through convenience, such as allowing administrators to manage devices from anywhere, or through overlooked defaults. It can also happen when the network lacks a dedicated management zone and administrators use everyday workstations for elevated tasks. The key beginner insight is that administration is a different trust level than regular use, and it deserves its own tight boundary. If you hear that administrators manage critical systems from the same zone where email and web browsing happen, that is a strong hint of architectural risk. A seventh misconfiguration is treating internal services as if they do not need protection because they are not internet-facing. Internal traffic can still be intercepted or abused if an attacker gains a foothold, and internal only does not mean safe. This is why encryption between internal services matters and why access should be authorized based on role, not merely on location. If sensitive systems accept connections from any internal source, they are trusting the network too much. If services are not authenticated to each other, impersonation becomes easier. This does not require you to become an encryption engineer today, but you should recognize the architectural principle. Internal communications should still be protected because the interior is not automatically trustworthy. The recall cue is that assumed breach is not pessimism, it is preparation. Now let's pull all of this into a spoken mini walkthrough that you can replay in your head. Picture a user laptop in a user zone, browsing the web and using business applications. That laptop should have limited ability to initiate connections to server zones, and most internet access should be visible and governed through controlled pathways. Picture an application zone that hosts services needed by users and a data zone that contains sensitive storage or databases. The application zone may need to talk to the data zone, but the user zone should usually not talk to the data zone directly. Then picture a remote user connecting through a gateway, entering a restricted remote access zone, and only then reaching specific applications based on role. Every one of those crossings should pass through an enforcement point that has clear policy and generates useful logs. If any part of that story becomes, and then everything can talk to everything, you have found a misconfiguration. In conclusion, spaced retrieval for network security architecture is about being able to narrate controls and misconfigurations without hesitation. Segmentation and security zones define where boundaries should exist, while firewalls, proxies, and remote access gateways enforce policy at those boundaries and provide visibility. Zero Trust ties these ideas together by treating trust as conditional and by pushing access decisions to be explicit, narrow, and continuously evaluated. Common misconfigurations tend to flatten boundaries, broaden permissions, weaken outbound controls, expose management access, and reduce logging to the point that misuse becomes hard to detect. The simple decision rule to carry forward is this: if a compromise in one place can easily spread to many places, the architecture needs clearer zones, tighter pathways, and better enforced boundaries.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.